Yes, sir.
Okay. Okay. Yeah. So, if you see what we were discussing in the last class was, uh, you know, we are in the hydraulic design of spheres, and then while talking about different aspect of that, we discussed about minimum velocity or self-cleansing velocity. There are few more salient features which I would like to mention over here. As far as minimum velocity or self-cleansing velocity is concerned. So what we have mentioned in the last class, if you see that basically, self-cleansing velocity is that velocity which should be maintained once in a day at least, so that you can ensure that no deposition is taking place within the sphere. So the next point is hence for removing the impurities present in sewage. In case of sand, the diameter is up to 1 meter with a specific gravity 2.65 and organic particles up to 5 millimeter diameter with specific gravity 1.2. It is necessary that a minimum velocity of about 0.45 meter per second and an average velocity of 0.9 meter per second should be developed in spheres. So this velocity you can calculate from the equation which has been given before. So these are the Vs value which I am talking about. Next is, hence while finalizing the sizes and gradients of the spheres, they must be checked for the minimum velocity that will be generated at minimum discharge. Fine. So about one third of the average discharge. So uh, main idea is to ensure that once in a day you can achieve that self-cleansing velocity, so that things are smooth, all the operations are smooth, and then there is no deposition which is happening. Apart from that, while designing the spheres, the flow velocity at full depth is generally kept as 0.8 meter per second or so. Now, spheres are generally designed for half to three-fourth full. We don't usually design it for full or 100% full. So the velocity at design discharge will even be more than 0.8 meter per second. So thus the minimum velocity generated in spheres will help in many ways. The first one is adequate transportation of suspended solids. Since we are talking about sphere, so that is going to convey um, liquid which will be carrying a lot of suspended solids, and you can if you can achieve your self-cleansing velocity, you can ensure that adequate transportation of suspended solids are happening through the spheres, keeping the sphere size under control. So obviously that is another one reason, to fulfill all the criteria. If you enlarge the size of the sphere, so that has a lot of problem associated with bigger dia sphere. We discussed it before as well. So that is why, to minimize, or let us say to optimize the sphere size, it helps to check for the self-cleansing velocity. Next, preventing the spheres from decomposition by moving it faster, thereby preventing evolution of foul gases. So that is another one aspect. If you the velocity of the sewage is less, then what will happen is decomposition will start happening during the conveyance itself, and that will create a lot of emission of foul gases that can actually create corrosion in the sphere pipes or in the sphere lines. So we can ensure that nothing of these sorts are happening if we can maintain the self-cleansing velocity, or that is the minimum velocity. Fine. So next, what we are going to talk about is basically the maximum velocity or non-scouring velocity. So if you see the smooth interior surface of a sphere pipe gets scoured due to continuous abrasion caused by the suspended solids present in the sphere. So just try to imagine, the solid particles, they continue create an effect of abrasion on the inner surface. Just if you see an enlarged photo, you will be able to understand that you have particles, and it is continuously rubbing the surface, and thereby it is creating an abrasion effect. And that actually creates some changes or alteration in the quality of the interior surface or the smoothness. This covering and wear and tear of the pipe interior is much more pronounced at higher velocities. And the thing is, the more is the velocity, the chances of scour and wear and tear is more. Fine. And now this wear and tear of the square pipes will reduce the lifespan of the pipe and the carrying capacity. So our objective is to ensure the maximum life of the sewage systems which we are laying down, because it involves a lot of cost of construction. And then if we have, because of the faulty design, if this if section of the sewage system if has to be removed or changed, then it will again increase the overall cost of construction and as well as the cost of maintenance. And to avoid such situation, we should be focusing on the maximum velocities, since this has direct impact on the wear and tear of the sewage system or spare pipes. So, in order to avoid these complications, it is necessary to limit the maximum velocity that will be produced in the square pipe at any time. Fine. So this limiting or non-scouring velocity will mainly depend upon the material of the sphere, and its value are actually mentioned in the below table. You can go through that table. Depending upon the material of the spheres, we have a limiting velocity. So if you have the very coarse surface, then the velocity or the maximum velocity or the limiting velocity of the or the non-scouring velocity is minimum in case of the pipe material which has a rough surface. Fine. Now the problem of controlling the high velocities generated in the spheres mainly arises in the hilly regions, fine, where the available slope is more than what is required, and that actually create a situation where the velocity is you get is much more compared to what is desired. Now, and you cannot avoid it because the ground slope which is available is steeper. Now, in such places, it may therefore be required to limit the design gradient and to adjust the balance available head by constructing drop-through manholes at suitable places along the length of the sphere. So these drop-through manholes are actually, one appurtenances which are very important. So when we will be discussing about appurtenances, we will discuss in detail. But here you just remember that it is an appurtenances which facilitate the changes in the head or the changes in the elevation without causing significant damages or abrasion in the sphere's internal surface. So this is the way, in the hilly region, the extra available gradient is maintained or is taken care of. So now the important part is effects of flow on the mm, flow variation on velocity in a sphere. So uh, this part maybe I'll discuss. Just you need to listen to me, because from there the hydraulic characteristics of sphere will come into the picture. So effect of flow variations on velocities in a sphere is basically the discharge flowing through the spheres varies considerably from time to time. All of you know that. Hence, it again depends on the rate of consumption. So throughout the day, if you are analyzing, so the maximum discharge which you can get in a particular sphere will not be you know throughout the day. There will be certain times when you will have the maximum discharge. So that is why the variation is there and which is significant, fine. Hence there occur variation in depth of flow and thus variation in hydraulic mean depth, and this is very true. Now if there is a difference in the discharge, so that will directly create an alteration in the value of hydraulic mean depth, and due to the change in the hydraulic mean depth, there occur changes in the flow velocity, because it is proportional to the hydraulic mean depth, or two-third of hydraulic mean depth. All of you know that if you go back and try to understand the equations which we discussed, in I guess in last class or last to last class, I don't remember exactly, where we talked about Manning's formula. So if you remember that, then you'll be able to understand that the velocity is proportional to r to the power two-third. And the same thing actually I am mentioning over here. Fine. So that is the influence of flow variation to the velocity, and therefore it is necessary to check the sphere for minimum velocity of about 0.45 meter per second at the time of minimum flow. That is one-third of the average flow I mentioned before, and the velocity of about 0.9 to 1.2 meter per second should be developed at a time of average flow. So these are the values which are very important, and it should be remembered. The velocity should also be checked for limiting velocity, that is non-scouring velocity at a maximum discharge. So this is very important. Now for flat ground spheres, are designed for self-cleansing velocity at maximum discharge. This will permit flatter gradient for spheres, and which is good in one way. Now, for mild sloping ground, the condition of developing self-cleansing velocity at average flow may be economical, whereas in case of hilly areas, spheres can be designed for self-cleansing velocity at minimum discharge, but the design must be checked for non-scouring velocity at maximum discharge as well. Now, these are the different aspects which actually you should be remembering. Now, with this, the next important part what we are going to talk about is the hydraulic characteristics of circular sphere sections running full or partially full. So in this case, if you see, I have directly mentioned the depth of partial flow D. So if you start from the area of cross section, so for that particular figure, the area of cross section of the entire sphere pipe would be pi by 4 into d square, right? A equals to pi by 4 into d square, where d is the diameter of the pipe. All of you know it is mentioned in the figure as well. So d, I'm talking about capital D. Now if I say the weighted perimeter, so the weighted perimeter is p, capital P, is equals to pi into d. Fine, pi into d. So now if we want to calculate the hydraulic mean depth, so what do we get? We get small r equals to a by p. So a, all of you know, right? A is basically, or which I have mentioned sometimes back, pi by 4 into d square, and weighted perimeter capital P is pi d. So if you put that, then you get a value of d by 4. Fine. Now that is when the sphere, when the sphere is running full and you have a circular section. So in that case, whatever I have told is correct. So it is quite easy. A is basically pi. All of you can calculate this, right? Are you able to understand what I'm telling? Are you able to understand what I'm telling?
Yes, sir. Yes, sir. Hello.
Yes, yes, I'm able to hear.
Yes.
Is it true for all the people? I can ask any one of you who are present in this class. Should I ask this? How many of you are able to understand? Should I ask any one of you? Or if you have any problem in understanding, you can tell me, because this part is very important to understand. Anyway, if you remain non-responsive, I have no problem. It's you are in loss, or not I am. Fine. So anyway, in that case, when circulars were running in full, then if you need to calculate the hydraulic mean depth, that is the r, small r, so that is basically equals to a by p, which we have mentioned before. So you can directly get the value d by 4, capital D by 4. Now when the spheres run partially full at a depth, let's say the small d, which I have mentioned in this particular figure, then in this case the depth at a partial flow would be given over here, d equals to d by 2 minus capital D by 2 minus capital D by 2 cos alpha by 2. And you can simply derive these things from the geometry, and you will end up getting what I have written over here. Now where alpha is the central angle in degrees, that is also mentioned, shown over here in this particular figure. So alpha is also known to you people. Now, once you get that d, small d, now you can get the proportionate depth. So proportionate depth is small d by capital D. So our small d is shown over here. That is for partially full conditions, and this d by d proportionate depth will be equals to 1 by 2 within whole bracket 1 minus cos alpha by 2. You see how we are actually calculating things. Now the next part is area of cross section while running partially full. So you need to calculate the area of the partially full section. Fine. So that has been actually shaded with a dotted line. So what I'm trying to tell is this particular portion you need to calculate the area. So that area is basically a is equals to pi d square by 4 into alpha by 360 minus d by 2 cos alpha by 2 and d by 2 cos sine alpha by 2. So basically these are nothing but geometry. You take proper geometry and then try to subtract things, and finally you end up getting the value of pi d square by 4 within whole bracket alpha by 360 minus sine alpha by 2 pi. Now, you may have some difficulties, but you need to tell me. In that case, I will be deriving these things in subsequent classes. I can do that. Now, once you get the small a value and you know the capital A value, that is the area of the cross section for the condition of running full. Fine, running full. So in that case, area is known to all of us, pi d square by 4. Now if we need to get the proportionate area, so it will be capital A small a by capital A. So pi d square by 4 gets cancelled out. So we get in the end alpha by 360 minus sine alpha by 2 pi. So that is what has been written over here as proportionate area. You can check it over here. In this place we have written it. Next, the proportionate perimeter, that is also we need to calculate. So proportionate perimeter, so capital P is known to us, that is pi d, and small p is pi d into alpha by 360, obviously. So if you want to calculate the proportionate perimeter, it will be pi d gets cancelled out, so you will have alpha by 360 only. Fine. Now accordingly, if we calculate the proportionate hydraulic mean depth, so what you need to do is, for running partially full, you need to calculate the small r, so that is small a by small p. So small a you have already derived, and small p also you have already derived. So if you do that, you end up getting d by 4 into this particular term. Fine, d by 4 into this particular term. Now if I ask you to calculate the proportionate hydraulic mean depth, that becomes small r by capital R, and basically your capital R is d by 4, which we have calculated before, or I have discussed before. So once you do that, you get r by so your proportionate HMD would be one in your d by 4 gets cancelled out in this case, so you get 1 minus 360 sine alpha by 2 pi alpha. So that is the proportionate hydraulic mean depth. Next, and the final one is proportionate velocity. So for this, what needs to be done is you need to apply Manning's formula, or maybe any of the formula which we have discussed it before. So usually Manning's are preferred to be used in this case. So what you need to do is, for partially full condition, you need to calculate the small v value. So that is, 1 by n r to the power 2/3 root s z 0. And when the running full condition, the velocity capital V would be 1 by capital N r to the power 2/3 root A0. A0 remain constant whether the pipes running full or partially full. I hope you are able to understand, because the S0 is nothing but the slope, bed slope. So bed slope cannot change with the change in the flow condition, that is running full or partially full. So bed slope remains constant, so the value is similar for both of them. Now if we have to calculate the proportionate velocity, so that becomes small v by capital V, which is shown over here. You can see in the last, that is number F. So then it becomes, capital N into r to the power 2/3 by small n into capital R to the power 2/3. So this is the way we can calculate, different uh, different we can calculate the different parameters. And then finally, once you, now if you assume that the roughness coefficient is also same and it does not change with respect to depth, then you can take small n is equal to capital N, then the things become more simpler. So proportionate velocity would become, in that case, so your n by n gets cancelled out. So you will have small r to the power 2/3 by capital R to the power 2/3. Now the small r by capital R is what you have already calculated, right? That proportionate HMD. The small r by capital R is nothing but the proportionate HMD, which has been calculated before. You see over here, proportionate hydraulic mean depth. So that in that case, once you assume that capital N equals to small n, in that case, you can basically write this proportionate velocity as r by r to the power 2/3, and then you can put the value of r by r, that is 1 minus 360 sine alpha by 2 pi alpha to the power 2/3. So that becomes your proportionate velocity. Hope all of you have understood. If you do not understand, please let me know. I'll derive them again. Now, discharge is the next parameters which we are going to talk about. So to calculate the proportionate discharge, we first understand the discharge for running full condition and partially full condition. So when running full condition, then discharge Q equals to capital A into V. So all of you know the expression for capital A, and as well as for capital V. On the other hand, for running partially full, it is small q equals to small a into small v. We have also discussed the expression for small a and small v, and if you put that in your equation, you get alpha by 360 minus sine alpha by 2 pi into 1 minus 360 sine alpha by 2 pi alpha. Now what you need to remember is, in all the above derived equations, whatever we have discussed till now, except alpha, everything is constant. And see, nothing is changing, right? Because other things remain same, because the pipe is same, the square diameter is same, the material is same, everything is same. Only the flow condition is changing. Therefore, the value of alpha is changing, and hence, by giving different values of alpha, all the 6 proportionate elements can be easily calculated. That is so true. You change your alpha value, you get for different alpha, you get different values of all those proportionate parameters, 6 parameters which we discussed. So those proportionate 6 parameters are actually given over here. A B C D E F, you can check. So So if you see here, these values. Now, what we can do is these values of hydraulic elements can be obtained from the proportionate graph prepared for different values of d by d. So basically, taking the proportionate depth, that is d by d, as reference, values of other elements can be can be found out from the tabular form. These tables are actually available in all the textbooks, and so directly you can use those tables. Knowing the value of d by d, you can get all the different values. Fine. So uh, I don't have that table. You can go through any textbook, you will get that table. So corresponding to d by d value, we have all other five parameters. And now, here another important point is the value of Manning's n can be considered constant for all the depths here. In reality, it varies with the depth of flow, and it may be considered variable with the depth, and accordingly the hydraulic elements values can be read from the graph for different depth ratio of flow. So this is very important, this depth ratio. So we are going to see what are the different figure which are available over here and needs to be considered. Okay, you can see that figure in the left hand side. We have depth d by d ratio, and with respect to that, we have different q by q value and v by v value. So knowing the value of d by d ratio, you can get the other obtained value, and in between also you can see that q by q for n by n variables. So for different n by n value, you can directly take, and accordingly you will get q by q as well as v by v. Similarly, in this case, so the first one is for running full, and the second one is for, but you have that two different. So the first one is the standard chart for proportionate hydraulic mean depths for circular spheres, and the second one is the proportionate elements to ensure self-cleansing velocity equivalent to full flow in circular spheres. So mostly we'll be using the first figure which have been mentioned in the left hand side, and accordingly we'll be calculating the other parameters. Fine. So if you see here, uh, the spheres flowing with depth between 50 to 80% full need not to be placed on steeper gradient and to be used as self cleansing as spheres flowing full. So this is very important point. The reason is that velocity and discharge are function of tractive force intensity, which depends upon friction coefficient, as well as the flow velocity generated by the gradient of the sphere, which is mentioned as subscript s. So ss by s. So this s is denoted for self-cleansing velocity equivalent to equivalent to that obtained in full section. The required ratios of Vs by V, Qs by Q, and Ss by S can be computed. Fine. So remember here, if we go and check the next slide. So what is in this case, if you get the proportionate, if you want to get the proportionate velocity for self-cleansing velocity, if you want to derive, then your V becomes Vs and the rest of the parameters remain same, and As becomes Ss. So for substituting the value of R by R equals to S by S, what we get is Vs by V equals to N by N into R by R to the power 1 by 6, and accordingly we can get the final value. So this is the entire procedure by which we actually calculate from this graph, and as well as, so basically this graph whatever we have shown over here, the first graph is nothing but, here if you see, the first graph is nothing but the against the d by d value. If I calculate in tabular form the proportionate area, proportionate weighted perimeter, proportionate HMD, proportionate velocity, and proportionate discharge. So the same things if I want to plot in the graph. So in that case, we get this graph which I have shown over here. Fine. So this is the left hand side one is a standard chart for proportionate hydraulic elements for circular spheres. So from the d by d ratio, you can get all other parameters. Fine. So in the exam, you may get these two chart, or directly, the proportionate elements which are required for your uh, you know calculation. You can either it will be given or provided directly, or it will be, these graphs will be given to you. From there, from these graphs you need to take out the values, knowing the value of d by d. So take this particular problem and try to solve it out. It will help you understand better. So write this problem as quick as possible. Write this problem. And any of the CR, let me know once you complete writing this problem. Is it done? Have you completed writing this problem? Sorry, I'm unable to hear you. Hello?
I'm telling yes, sir, you have completed.
It's not clear what you're.
Some network issue on my side.
Anyway, I'm unable to hear. Anyone else can speak? Is it done?
Yes,
Hello?
yes,
Yes, sir, it is done, so you can carry on.
Okay, fine. So try to solve this problem. If you have any difficulties, you can ask me in the next class. Uh, but if you have understood what I discussed, I guess there should not be any problem. And at the same time, I have already given all the required values. So with corresponding with respect to d by d value, p by a and r by r also given. So there should not be any problem. However, you should practice this to have better idea. Fine. So in the next slide, basically we are going to talk about the shapes of different type of spheres. So the first one is circular shaped spheres, and this sphere is most widely used for mostly all types of spheres, and this is the most common one, and that is why you might have noticed that in case of all the hydraulic design, we usually take circular spheres, and then accordingly we practice the entire design procedure. So that is why this is the most common one, and these are the you will see that throughout the country in most of the cases we have circular sphere which have been utilized. Next is standard egg-shaped sphere. Now these egg-shaped spheres are preferred in case of combined spheres sometimes. Uh, Now we can have different type of accept sphere, and any type of accept spheres are actually preferred in case of combined spheres. So any type of accept spheres. So this is what is important to remember. Since in this particular curriculum the design of these different type of shapes of spheres are not there, I'm not going to discuss those designs aspect. However, just to give you an idea about what are the different types and when we can use them, I am just mentioning things over here. Next is horseshoe shaped spheres. So these type of spheres are used usually for large spheres where you have higher discharge, and mostly for trunk and outfall spheres also. So mainly when the discharge is high, then these type of spheres are preferred, compared to the circular shaped spheres. Next comes the parabolic shaped spheres. So parabolic shaped spheres will have it consists of one invert, and they actually they can be used in case of smaller discharge sewage, and though this is not very common, but still you can see in some places, and they are usually used in case of smaller uh, discharge. Next is rectangular shaped section. So generally these are used in case of covered stormwater drains, as I mentioned. So in stormwater drains, we can consider them as open channel flow. However, we need a we sometimes we prefer putting a cover, and once we put a cover, then the section becomes a rectangular sections. And apart from that, we have semi-elliptical, we have U-shaped section, we have semicircular shaped section, but these are quite semicirculars and basket handles. These are quite obsolete these days. People don't use it. However, in case of large sphere, we can have U-shaped, but these days people prefer horseshoe-shaped sphere over U-shaped spheres in case of large spheres. So these are the different shapes of spheres which are very common and you can see in practice, and their name as well as where we can use these particular type of spheres. You need to remember these things, and with this, I'll stop today's class. We'll discuss the next part in the next class.